All right, welcome back. Okay, so we're going to start talking about series now, something that maybe you're a little familiar with from pre-calculus. More specifically, we're going to talk about convergent and divergent series. Divergent in the background, hilarious. Okay, so suppose that I am hanging out on a 1 mile field, as I often do, and I decide to walk halfway across that field. And then from that point, I want to walk then half the distance from where I am to the other end. So in other words, I'm walking just a quarter of the way across the field, and then I just keep walking halfway and halfway and halfway and halfway. Of course, I'll never reach the other side, but I can get as close as I want. So what I'm doing here is I'm adding a half plus a quarter plus an eighth plus a 16th, and so on. If I kept doing this forever, this would turn into an infinite sum, which I'm using sigma notation here to write. This is the sum as n runs from 1 to infinity of 1/2 raised to the power of n. What is this equal to? Has anyone seen this before? Oh yes, correct. This is equal to 1. This sum, even though I'll never actually get all the way across the field, if I could take an infinite number of steps here, then I would eventually get to the other end. I'd have to do it for an infinite amount of time, though. The limit is 1. We would say that the limit is 1. So this was an example of a geometric series, something that you've probably seen before. But more importantly, this is an example of what is known as a convergent series. It's convergent because you're adding up an infinite number of things, but your sum is not infinite. Your sum is converging to a certain value. We're getting closer and closer to the value of 1, in fact, which is pretty cool. You don't have to converge to 1. You could converge to any number that you like, for instance, 94. But it has to be to some finite number. That's the key in order to be a convergent series. Mathematically, this is more complicated. We say that a series converges if the limit of its partial sums exist. So in the last example, what do I mean by partial sums? So S1, the first partial sum, would just mean add the first term. So just write the first term. S2, the second partial sum, would be 1/2 plus 1/4. I would add the first two terms. The third partial sum would be 1/2 plus 1/4 plus 1/8, and so on. Dot, dot, dot. And what you'll see is that these numbers that you're getting are getting closer and closer and closer to 1. And in fact, you can calculate that limit pretty easily. We might do that in class. But that limit is 1, so that's why we say that the series is converging. More specifically, is converging to 1. If this is not happening, if you're not getting closer and closer to one certain number, maybe you're bouncing back and forth between two different numbers, or maybe your number is just growing larger and larger without bound, meaning it's going off to infinity. If any of those things happen, then we say that the series diverges. That would be the opposite of converging. You're diverging. You're not getting closer and closer to a single value. The limit does not exist, in other words. Okay, cool. So that's a fun example of a convergent series. What would happen, let me pose this to you, you can probably guess what's going to happen here. Suppose that I want to add the reciprocals of every positive integer. What would I get? What would you get if you added up the reciprocals of every positive integer? So of course what I mean by this is you're going to add 1 over 1, which is 1, to 1/2, to 1/3, to 1/4, to 1/5. You're going to add all the reciprocals of the positive integers. Your infinite sum would look like this, right? We're adding up 1 over n, as n ranges from 1 all the way to infinity. So we know what the sum is off the top of their head? No? Cool. Well, let me, I claim that the sum is actually infinite. This is a divergent series. It's called the harmonic series. But it's divergent. It runs off to infinity. It keeps getting larger and larger and larger without bound, which is a little bit of a bummer. Why is that true? I'm glad you asked. Well, suppose that it is, in fact, a finite number. And I'm going to call that finite number S for sum. So S is equal to 1 plus 1/2 plus 1/3 plus blah, 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 blah until forever. I claim that this infinitely long sum is greater than or equal to this infinitely long sum. Do you all see what I've done here? Basically, I'm just saying that so 1/3 is, of course, bigger than 1/4. 1/5 is, of course, bigger than 1/6, and so on. I mean, the next terms that you would see here, this would be 1/7, and then plus 1/8. And this would be 1/8 plus 1/8. But 1/7 is bigger than 1/8. And so everything else is the same, though. So of course it's greater than or equal to. In fact, we could even say it's just simply greater than. But it's a little bit dangerous to say simply greater than because, this is going off forever. So we don't know if it's just greater than or if it's greater than or equal to. It could be equal to. We don't really know. So we're just covering all of our bases. It's greater than or equal to this infinitely long sum. Well, by some clever grouping here, for instance, what you'll notice is I'm putting these two 1/4 together to give me this 1/2. And I'm putting these two 1/6 together to give me this 1/3. And the next two 1/8 are going to go together to give me 1/4. And so on. So this is going to go on forever. And so what you'll notice is that this infinitely long sum is equal to 1 plus 1/2 plus 1/2 plus 1/3 plus 1/4 plus 1/5 until forever. So you see this is looking exactly like our sum that we started with, except there's an extra 1/2 here. There's an extra 1/2 in this term. So this is equal to my original sum plus 1/2. Is it making sense? Do you see what the problem is here? Do you see what went horribly wrong? We just showed that S is greater than or equal to S plus 1/2. Is there any number where if you add a half to it, it gets smaller? That's nonsense. This is insanity. This is the symbol in mathematics for contradiction. This is crazy. You can't have a number that's greater than or equal to that number plus 1/2. If you add 1/2 to a number, it gets bigger, folks. I hate to tell you. So this means that there can be no S. This doesn't make any sense. The only way this would be true is if S is infinite, because infinity is in fact greater than or equal to infinity plus a half, because infinity plus a half is still infinity. So there's no way that S can be a finite number, so therefore this is a divergent series. So sad. Suppose that instead of adding the reciprocals of every positive integer, I want to add the squares of the reciprocals of every positive integer. In other words, I want to find this infinite sum. The sum as n goes from 1 to infinity of 1 over n squared. Is this one going to be convergent or divergent? What do you think? Alright, if you guessed convergent, you were correct. And even more exciting than that, something that we'll be proving in class very soon, is that this sum is actually equal to pi squared over 6. It's kind of crazy. You can calculate a bunch of partial sums here. Add up like the first 10 terms, and you'll see that you're very, very close to pi squared over 6. And you're going to keep getting closer and closer to pi squared over 6. You'll never quite get there unless you went on forever. But that is the limit. And since that is a finite number, this is a convergent series. Pretty exciting stuff. In fact, any time that the exponent of the denominator there, so you see how I've got 1 over n squared here, 1 over n squared right there, for the harmonic series, which is 1 over n, so in other words 1 over n to the first power. In general, if you have 1 over n to the power of p, this series is going to converge if p is larger than 1. If p is smaller than 1 or equal to 1, then it diverges. When p is equal to 1, we get the harmonic series, and if p is any smaller than 1, everything's going to fall apart as well. Cool. Well, hope you enjoyed this. Thanks for tuning in, and I'll see you soon.